Today is Wednesday, August 31st, 2022. So today is a hump day and also the last day of August. Coming up, we have a Chuseok holiday. There's a lunar harvest holiday or Thanksgiving Day of Korea in the early part of September. So this year will pass really quick. So just really quick, like wind. Here's an interesting article about wind turbine blade design. I studied mechanical engineering, so I am interested in the design of the blades, especially the design of the airplane, which is quite simple, and also design of the nozzle of the rocket, or the exterior design of the rockets, or any propellants. Or anything in the space. So take a look into this article as I read it as a part of my daily English reading exercise. I'm trying to focus on the key expressions, words that I would like to remember. And this is purely academic effort, no intention of despising people or infringing on the patents or copyrights. It's just purely academic. Wind turbine blade design. Should wind turbine blades be flat, bent, or curved? The wind is a free energy resource until governments put a tax on it. But the wind is also a very unpredictable and unreliable source of energy, as it is constantly changing in both strength and direction. It is constantly changing in both strength and direction. So to ensure we get the most out of the available wind energy, it is important that the wind turbine blade design be of an optimal performance. To produce useful amounts of power, wind turbines generally need to be large and tall. But to work efficiently, they also need to be well designed and engineered, which makes them expensive too. Most wind turbines designed for the production of electricity have consisted of a 2 or 3 bladed propeller rotating 2 or 3 bladed propeller rotating around the horizontal axis. It's obvious to say that these propeller-like wind turbine blade designs convert the energy of the wind into usable shaft power called torque. This is achieved by extracting the energy from the wind by slowing down or decelerating the wind as it passes over the blades. That's another good term, accelerating, decelerating. The forces which decelerate the wind are equal and opposite to the thrust-type lifting forces which rotates the blades. The forces which decelerate the wind are equal and opposite to the thrust-type lifting forces which rotates the blades. Just like an aeroplane wing, the wind turbine blades work by generating lift due to their curved shape. The side with the most curve generates low air pressure, while high pressure air beneath pushes on the other side of the blade-shaped aerofoil. The net result is a lifting force perpendicular to the direction of flow of the air over the turbine's blade. The trick here is to design the rotor blade in such a way as to create the right amount of rotor blade lift and thrust, producing optimum deceleration of the air and therefore better blade efficiency. Decelerating. If the turbine's propeller blades rotate too slowly, it allows too much wind to pass through undisturbed and thus does not extract as much energy as it potentially could decelerate undisturbed. On the other hand, if the propeller blade rotates too quickly, it appears to the wind as a large flat rotating disk, which creates a large amount of drag force perpendicular. When the optimal tip speed ratio TSR, which is defined as the ratio of the speed of the rotor tip to the wind speed, depends on the rotor blade shape profile, the number of turbine blades, and the wind turbine propeller blade design itself. So which is the best blade shape and design for a wind turbine blade design? Generally, wind turbine blades are shaped to generate the maximum power from the wind at the minimum construction cost. But wind turbine blade manufacturers are always looking to develop a more efficient blade design. Constant improvements in the design of wind blades has produced new wind turbine designs which are more compact, quieter, and are capable of generating more power from less wind. It's believed that by slightly curving the turbine blade, they are able to capture 5 to 10% more wind energy and operate more efficiently in areas that have typically lower wind speeds. Wind turbine blade design. So which type of blade shape would produce the greatest amount of energy for a wind turbine? Flat blades are the oldest blade design and have been used for thousands of years on windmills. But this flat broad shape is becoming less common than other types of blade design. The flat blades push against the wind, and the wind pushes against the blades. The resulting rotation is very slow because the blades that are rotating back on the upstroke after the generating power are in opposition to the power output. What? The resulting rotation is very slow, obviously, because the blades that are rotating back on the upstroke after generating power are in opposition to the power output. This is because the blades are acting like huge pedals moving in the wrong direction, pushing against the wind, giving them the name of drag-based rotor blades, drag. However, flat blade designs offer significant benefits for the DIYer. Compare DIYer. That's good. We need to remember. See? DY apostrophe NER. DIYer. Compared to other wind blade designs, flat rotor blades are easy and cheap to cut from sheets of plywood and metal, ensuring that the blades have a consistent shape and size. They are also the easiest to understand, requiring less design and construction skills, but their efficiency and the ease of generating electrical power is very low. Curved blades are very similar to a long aeroplane wing, which known as an aerofoil, which has a curved surface on top, which is also known as an aerofoil, aeroplane wing, aerofoil. The curved blade has air flowing around it with air moving over the curved top of the blade faster than it does under the flat side of the blade, which makes a lower pressure area on top and therefore, as a result, is subjected to aerodynamic lifting forces which create movement. These resulting forces are always perpendicular to the curved blade's upper surface, which causes the blade to move, rotating around the central hub. Which causes the blade to move, rotating around the central hub. The faster the wind blows, the more lift that is produced on the blade, hence the faster the rotation. Okay. I got it. The advantages of curved rotor blade compared to a flat blade is that lift forces allow the blade tips of a wind turbine to move faster than the wind is moving, generating more power and higher efficiencies. As a result, lift-based wind turbine blades are becoming more common now. Also, homemade PVC wind turbine blades can be cut from standard-sized drainage pipes, having the curved shape already built in, giving them the best blade shape, curved blade airflow and performance. Angle of attack, yes, angle of attack, curved blade, aerofoil, airplane wing, low pressure. The wind moves so fast, right? Wind moves so fast, faster than here. Someone says this blade will cut the air pocket here, so that and the air pocket will meet again here, so that the air here needs to move faster because it follows the longer path. So that's why the air speed is fast, and fast speed in the fluid dynamics means low pressure according to Bernoulli dynamics. Lift, high pressure, curved blades. But the curved blades also suffer from drag along its length, which tries to stop the motion of the blade. Drag is essentially the friction of air against the blade surface. Drag is perpendicular to lift and is in the same direction as the air flow along the blade surface. But we can reduce this drag force by bending or twisting the blade and also tapering it along its length, producing the most efficient wind turbine blade design. The angle between the direction of the oncoming wind and the pitch of the blade with respect to the oncoming wind is called the angle of attack. Angle between the direction of the oncoming wind and the pitch of the blade with respect to the oncoming wind is called the angle of attack. As this angle of attack becomes larger, more lift is created, but as the angle becomes even larger, greater than about 20 degrees, the blade will begin to decrease lift, blocks the wind. So there is an ideal pitch angle of the rotor blade that creates the best rotation, and modern wind turbine rotor blades are actually designed with a twist along their length from a steep pitch at their root as a very shallow pitch at their tip. As the speed at the tip of a rotating blade is faster than it is at its root or center, modern rotor blades are twisted along their length by between 10 to 20 degrees from root to tip, so that the angle of attack decreases from where the air is moving relatively slowly near to their root to where it is moving much faster at the tip. This blade twist maximizes the angle of attack along the length, getting the best lift and rotation. In conclusion, the wind turbine's rotor blade length determines how much wind power can be captured as they rotate around the central hub, and the aerodynamic performance of wind turbine blades is very different between a flat blade and a curved blade. Flat blades are cheap and easy to make, but have high drag forces, making them slow and inefficient. To increase the wind turbine blade efficiency, the rotor blades need to have an aerodynamic profile to create lift and rotate the turbine, but curved aerofoil type blades are more difficult to make, but offer better performance and higher rotational speeds, making them ideal for electrical energy rotation. But to obtain the best design for wind turbine blades, we can improve the aerodynamics and efficiency even more by using twisted tapered propeller type rotor blades. So twisted tapered propeller type rotor blades. Twisting the blade changes the wind's angle along the blade with a combined effect of twisting and tapering the blade along its length improves the angle of attack, increasing speed efficiency while reducing drag. Also, tapered blades are stronger and lighter than straight blades as the bending stress are reduced. Wind turbine blade design is crucial in order to make a wind turbine work as per the expectations. Innovations and new technologies used for designing wind turbine blade have not stopped here, as new formulas and designs are being considered to improve their performance, efficiency, and power output daily. To learn more about wind turbine blades and how they work as part of wind power system, then click here to order your Wind Power for Dummies book from Amazon today and find out more about wind turbines, wind energy, and wind generators for generating your own free power before the government starts to tax on the wind energy. So there's quite a technological article. I studied mechanical engineering and also the aerodynamics for a year in my undergraduate study, fluid dynamics in other words. But this one, I need to think about the design. This one generally is true, but I wonder, so the wind comes here and wind blade design, so wind, it will rotate and produce a lot of power. So this one should be tapered, obviously. It cannot be like this shape. This angle of attack is also very important. This article is very expounding, informational, not that much of technological terms, but it provides good insight how to design the angle of attack and their tapering and flat design and so on. Flat design, I'm not sure if it produces drag. When I think of windmills, it's just a flat blades attached to the rotating shaft, and it produces it almost blocks the air, but I'm not sure if the rotors at the bottom, when they pass the bottom part of the windmill, produces more drag. I'm not sure about that. I think the drags are produced on each blade almost at the same strength and speed and same magnitude. I have to think about that. Anyway, the several terms, expressions that I would like to remember is airplane wing, airfoil, tapering, angle of attack, lifting force, lift, perpendicular, of course, perpendicular to angle of attacks, design, propeller, blades, blade or blades, shaft, wind, power, tax. Government begins to tax on wind energy resource, secure, no secure. Yeah, I think that's just about it. Flat design, curved design, flat design, curved design, wind speed, wind energy. Yeah, this is purely academic English effort, learning or practicing effort. I think I will read this article one more time in later video session. Thanks for listening. Bye bye.